Have you ever stopped to think about how your code, something you write in a very human-friendly language, actually turns into something a computer can run? It feels a little bit like magic, right? But it's not. Turns out, it's all thanks to a really crucial piece of software, the compiler. So let's just get right to it. The big question. How on earth does your computer, this machine that literally only understands ones and zeros, make any sense out of the code we write? Okay, take a look at this. On one side, you've got a line of code that's pretty easy for us to read, right? Result equals rate times 60. Makes sense. But on the other side, well, that's what the computer's processor actually sees, just a whole bunch of ones and zeros. That is the huge gap, the great divide that we somehow need to bridge. So, how do we build that bridge? Well, that's where the compiler comes in. It's really the hero of our story. You can think of it as this incredibly smart, expert translator. Its whole job is to take our code, the stuff we write, and meticulously convert it into the language the machine understands, and hey, it even checks for mistakes along the way. And this right here, this is iconic in the world of computer science. It's the cover of what's probably the most famous textbook on compilers ever written, famously known as the Dragon Book. And it gives us this awesome metaphor that we're going to run with. The idea is that building a compiler is like slaying a dragon. The dragon? That's the insane complexity of a programming language. And the compiler? That's our knight in shining armor, ready to tame that beast. All right, so here's the game plan. We've talked about the Great Divide, and we've met our dragon-slaying compiler. Next up, we're going to peek inside that black box. We'll see how it first understands our code, then how it actually builds the program, and finally, we'll talk about why this whole dragon-slaying thing is so important. All right, let's do it. Time to crack open that black box and see what's really happening in there. And you'll see, it's not just one simple step. It's a whole, carefully planned out process. So, you can basically think of a compiler as having two main parts. First, there's the front end. Its job is all about analysis, breaking down our code to figure out its structure and what it actually means. It's kind of like how you'd read a sentence and figure out the nouns, verbs, and the overall meaning. Then you've got the back end. Its job is synthesis. It takes that understanding from the front end and actually builds the final program. Sticking with our analogy, this is like taking the sentence you understood and translating it perfectly into another language. Okay, so let's dig a little deeper into that first part, the front end. This is where all the analysis happens, where the compiler really learns to read our code. And to make this super clear, we're going to follow one single line of code all the way through its journey. And here's our line of code. Pretty simple, right? Just a basic calculation. We're going to watch step by step as the compiler takes this, pulls it apart into its most basic pieces, and then puts it all back together as something the computer can actually execute. First up, we have what's called lexical analysis. Now, what does that mean? Well, the compiler literally reads our code one character at a time and groups them into these little chunks called tokens. You can think of it exactly like reading a sentence and identifying each word and piece of punctuation. It's just figuring out what the basic building blocks are. And this is what you get. Our line of code is no longer a string of characters. It's now a stream of these tokens. So you can see the variable names, position, initial, and rate are now just generic identifiers. Let's call them ID1, ID2, and ID3. And the equal sign, the plus sign, the star, and even the number 60, they're all their own separate tokens now. All right, next up is syntax analysis. The compiler takes that stream of tokens we just made and uses it to build a tree structure. This is called a syntax tree, and it's all about representing the grammar of the code. It's basically checking to see if our programming sentence follows all the rules and is put together correctly. And what's so cool about this syntax tree is that it's not just a list, it actually captures the relationships between things. You can literally see how it understands that rate has to be multiplied by 60 before that result gets added to initial. It gets the order of operations right. And that's the key here. The structure reveals the meaning. Okay, so the grammar's correct, the structure's sound, but does the code actually make sense? That's what the last step of the front end, semantic analysis, is all about. This is where the compiler does a meaning check. Is everything logically consistent? Are the data types correct? For instance, this is where it would catch you if you tried to multiply a number by, say, a string of text. It's the step that finds the logical mistakes that grammar alone can't. And with that, the front end's job is done. The compiler now has a deep understanding of our code.
So let's switch gears and head over to the back end to see how it takes all that knowledge and actually builds the program. So, the first thing the backend does is create something called an intermediate representation. Just think of it as a generic, super simplified version of our program. It's not tailored for any specific type of computer just yet, and that's on purpose. It makes the whole process way more flexible. And here's what that looks like for our little line of code. You can see our one complex instruction has been broken down into a bunch of really simple, separate steps. Each line now does just one thing. This super clean format is the perfect playground for the compiler to work its magic in the next step. And now for maybe the coolest part of the whole process, code optimization. This is where the compiler puts on its thinking cap. It scours that intermediate code looking for any possible way to make it faster or smaller or just more efficient, all without changing what the code actually does. I love the analogy of a master chef who figures out a shortcut in a recipe that saves a ton of time but makes the final dish taste exactly the same. And just look at this. The compiler was smart enough to see that it could do some of the math with the number 60 right away and then combine a couple of steps. It took 4 instructions and boiled them down to just 2. That is awesome. Now, on its own, it seems like a tiny change, but imagine this kind of optimization happening millions of times in a big piece of software. That's how we get the incredibly fast and efficient programs we use every single day. Okay, we're in the home stretch now. The final phase is code generation. This is where the compiler takes that lean, mean, optimized code and translates it into the specific language of the target computer. This is the moment it becomes actual, runnable code that the hardware can understand. And there you have it. Our simple little line of code has finished its long journey. It's been completely transformed into a set of precise hardware instructions ready to use the processor's own super fast internal memory, what we call registers. But, the story doesn't actually end there, because it turns out that all these brilliant techniques for slaying the dragon of code complexity, well, they're useful for a lot more than just compiling programs. This technology is way bigger than just being a translator. I mean, think about it. The same kind of analysis we just walked through is used to build tools that hunt for bugs and major security holes in our code. The optimization ideas, they help engineers design faster computer processors. This stuff even powers tools that can translate code from, say, Python to C++. So when you really get down to it, understanding compilers is understanding the absolute bedrock of modern software. And that kind of brings us to a final question. We've just seen how compilers are built to tame the complex dragons of today's programming languages, but what about tomorrow? We're heading into a future with quantum computing, with AI that writes its own code, with unbelievably complex systems. The dragons are just getting bigger and scarier. So the real question is, what new dragon slayers are we going to have to invent to face them?